Hi, I'm Crispy. I hope you're doing well. Welcome back to Making the mangoPi, the series where I walk you through my PCB design process. Today we're going to go over the FPGA, how the Compute Module 4 can configure it, as well as the power for the board. Let's get started. This is the 7 Series FPGA Datasheet Overview. This is a good datasheet for getting a general feel about all the different FPGAs that are in the 7 Series family. If we scroll down a bit, we can get a better view about the FPGA that's on the mangoPi revision 3. This table can give you a pretty good idea about the features and capabilities of the FPGAs you're looking at. So if we go down to the XC7A35T row, then we can get some good information about the FPGA. The column immediately to the right is logic cells. Now I like to use logic cells just to give you a general idea about how big the FPGA is. For instance, the 35T version has about 33,000 logic cells, while the 200T version has over 200,000 logic cells. So it's significantly bigger. But to be honest, the projects that I'm planning to make with this board are never going to need 200,000 logic cells. If we go to the next column over, we have slices. Now, you can actually get a great idea about what is in your FPGA if you look at the notes down here. Each 7 Series FPGA slice contains 4 lookup tables, or LUTs, and 8 flip-flops. LUTs are basically how you implement logic in your FPGA, and flip-flops are used for storing bits of data. And the second part says, only some slices can use their LUTs as distributed RAM, or SRLS. I don't know what SRLS is, but I do know what distributed RAM is. Distributed RAM is basically taking these lookup tables and using them to store bits of data when they're really intended to implement logic in your FPGA. But nonetheless, it is still nice to be able to have extra RAM in your FPGA. The next column is the max amount of distributed RAM. As that note said, only some of the slices can use their lookup tables as distributed RAM, so that's where that number comes from. The column after that is DSP slices, which DSP stands for Digital Signal Processing. These are basically bits and pieces of the FPGA that are really good at doing math and working with floating point numbers. So that's what they're useful for. If we go to the next column, we get into the block RAM blocks, which these are pieces of the FPGA that are intended to act as RAM. And they're divided up into sections. So the 35T has 100 blocks that can hold 18 kilobits of information, and it has 50 blocks that can hold 36 kilobits of information. And in total, it can hold 1800 kilobits. Now, 1800 kilobits might seem like a lot of RAM, but let me ask you this. When's the last time you saw a 2 gigabyte thumb drive? I haven't seen one for years, but a 2 gigabyte thumb drive has 16 billion bits of data in it, or 16 million kilobits of data. This is 1,800. It's pretty small, but the really good thing about this block RAM is that it is very fast to access this. Now, not as fast as using distributed RAM, but still pretty fast. And now as we continue on, we start getting into the actual I/O features of the FPGA. So CMTs are related to the clocks. PCIe represents that there is support for one PCIe interface with the FPGA. GTPs are GTP transceivers, which are basically just special pins that can turn on and off or read data really fast. How fast? Well, a normal I/O pin on an FPGA could in theory read about 400 megabits of data per second. But these GTP pins can read over 6 gigabits of data per second, or 6,000 megabits of data per second. So 400 megabits per second versus 6,000 megabits per second. These things are really good at high-speed communication. The next column, we have the XADC blocks. XADC is the analog to digital converter that allows the FPGA to actually read analog signals. The next column is total I/O banks, which is 5. For this particular FPGA, there's an I/O bank 14, 15, 16, 34, and 35. Now, each of these banks can behave independent of each other. You can have one of those banks using 3.3 volt logic. You could have another one of those banks using 2.5 volt logic, and another one using 1.8 volt logic. Doesn't really matter. The last column is max user I/O, which goes back to how each of these I/O banks has 50 user I/O in it. So if you used every single I/O available in the device, then you'd have 250 I/O pins. Now, why do I want to make the revision 3 compatible with both the 35T as well as the 50T? Well, if you look at the table here, you'll see that on the logic side, which is pretty much everything to the left here, the 50T has roughly 50% more in every category, as in the logic cells goes from 33,000 to 52,000, the max block RAM goes from 1,800 to 2,700, but then everything on the input-output side, or the I/O, is the same. And this is nice because it makes it possible to not change anything on the board except for a few capacitors and be able to upgrade how much logic the FPGA or the mangoPi can represent in its FPGA, which is basically just expanding what type of projects you could take on with it without doing too much extra PCB engineering. And we like that. Underneath the FPGA is a ton of capacitors. Now these capacitors are known as decoupling capacitors. Their job is to remove fluctuations in the power supply to the FPGA. Tons of different things can cause fluctuations, and I don't understand most of them, honestly. All I know is that you want to have capacitors very, very close to the FPGA, especially these smaller ones that are meant to deal with very small fluctuations and changes in the power supply. But since we're adding the ability for this board to hold a bigger FPGA, we need to add a few more capacitors underneath the FPGA, which there's a datasheet for. There's datasheets for everything. It's but I don't think what people realize when you're doing PCB design or just like circuit design in general is that there is so much reading. Like this datasheet here just goes on. Okay, it's 19 pages, but hear me out. There's a lot of reading. This is the wrong one. This is the right one. So there's a datasheet dedicated to helping you design PCBs with the FPGAs, which is pretty sweet. So in this datasheet, there's this handy table here that has the recommendation from Xilinx for how many of those decoupling capacitors you need. So if we scroll down and find our package, which is the FGG484, then we find our device, which is the XC7A35T and the XC7A50T. Then we can just go across and figure out how many of those different voltage rails need capacitors and how many capacitors they need along with the values they have. So for instance, the XC7A35T does not need any 680 microfarad capacitors, doesn't need any 330 microfarad capacitors, but it does need one 100 microfarad capacitor on the VCC internal rail. And then you can continue on down this list and make sure that you have enough capacitors for the FPGA. But you'll notice that the XC7A35T and the 50T do not share the same amount and type of capacitors. As in, the 50T does need one 330 microfarad capacitor, but the 35T only needed a 100 microfarad capacitor. But here's what we're going to do. We're actually going to design the decoupling capacitors to be in specification with the 50T, because you really can't hurt anything by upping these capacitance values. Because once again, these are only recommendations, and these are actually based off of using the FPGA at a very high load. I think it's like 80% of the logic is within use. The 80% of the BRAM is in use. Using 50% of the clock generation bits of the FPGA, so stuff like that. So it really is just a recommendation, and by going with the safer recommendation of using larger capacitors and using more capacitors in the case of the 4.7 microfarad, where in the 35T you only need 2 of them, but the 50T you need 3 of them, it's not going to hurt anything. So long story short, we will be using the XC7A50T specification for how many decoupling capacitors to have on the board, even though we still want to be able to use the 35T version of it. So let's go add those capacitors right now. So this is the FPGA power page from the revision 2 of the board. I just straight copied and pasted it, and there's a few things we need to remove before we can actually add the extra capacitors. So down here we have a couple power supplies that will no longer be used because I am using two larger power supply integrated circuits, and these ones are no longer needed. So we're just gonna delete and remove these as well. So now we can actually add the extra capacitors. On VCC internal, we need to replace the 100 microfarad with a 330 microfarad. So VCC internal is right here, which is VCC int, and we have our 100 microfarad right here, so we're going to replace this with a 330. All right, sweet, did our first one. And now we're going to continue to the right. We see that on VCC internal, we also need an additional 4.7 microfarad. So we're going to pull this out. And then we can just do a nice copy paste. Oops. So there's our additional 4.7, which this reminds me, since I copy and pasted this from the revision 2, all the capacitor naming convention is messed up. So I'm going to have to go back and rename all these so they actually start at C1 and C2 and C3. Anyways, so we added the extra 4.7 microfarad. Now we need two extra 0.47s. So we can just move these along. And now we've taken care of VCC internal. We swapped out the 100 microfarad for a 330 microfarad, and we added a 4.7 microfarad, and then we added two 0.47 microfarads. So now I'm going to go ahead and add the rest of the needed capacitors. Super cool montage. VCC DRAM needs additional ones. This is like 20x speed. So VCC DRAM needs, it just needs the 47 to 800. And I'm writing the same. And that's it actually. Okay, that was easy. Beautiful. So I actually didn't need to do a cut there. It was literally changing this from a 47 microfarad to 100 microfarad. And now we've made the decoupling capacitors compatible with both the 35T and the 50T. So once again, I copy and pasted this from the mangoPi revision 2, so we need to remove some stuff and change some stuff before moving on. First things first, this is the flash module that was on the revision 2. Now flash is just a non-volatile storage, which means that when the board is powered off, it retains what it had in memory. So this is useful with FPGAs because you can store the configuration data in the flash so that when you power on the board, whatever was last loaded onto the FPGA will be automatically loaded onto it. Though I'm deciding to remove this because since you have the compute module on the board, you can load whatever bit stream you want to on power up. And you can even put more complex logic in there, like, hey, what time is it? Cool, load this bit stream. And you just do cool stuff with it. So there's really no need for it. And I need as much space as I can get. So bye-bye. Now that we've removed the flash memory, now we need to add the MCX connector, which I misspelled here, but that's okay. We place a component. Before this was just a normal 2-pin header, but that's not very useful, so so we'll do this instead. And now that we've replaced the MCX connector, we're actually done with this part, and we'll be leaving everything else the same. Now on to the actual configuration. So the FPGA is configured using a mode known as slave serial. But what is slave serial? Well, the first word slave means that the Raspberry Pi compute module will be supplying the clock during this configuration. And then serial means that there is only one data line. So basically what happens is the compute module 4 is using its SPI interface, which is the serial peripheral interface, to generate a clock signal, which will go into this CC clock pin here. And then there's one data line, which is the master out slave in line of SPI. and then that will go into a pin in bank 14. So we need to make sure that we have the Raspberry Pi's MOSI line going into D-in, which is this one here. And we go back to configuration now, and we no longer need this header here, so we can just remove that. And then you can take this, put that there, delete this, delete that. And now with the M1 and M2, so I think it's right. I don't know. Stuff, which is obviously. All right, so now that we got that cleaned up, I'll actually explain what the pins are doing. So going from the top down, the first 4 pins here are used for the JTAG interface. Now regardless what configuration mode the FPGA is in, you can still access these pins. So eventually I'll actually have these go out to a header and to the PCIe connector so that hopefully you could use your computer to program the FPGA, or your PC if it was plugged into it. Below that we have the C clock, which, as I mentioned, this is where the Raspberry Pi's SPI clock needs to go into, because the FPGA is the slave to the Raspberry Pi compute module. And next we have the M0, M1, and M2. Now these are used to tell the FPGA how it will be configured. So these actually have an internal pull-up resistor on them, so they are all high by default. And when these are all 1, that means that you want to use the slave serial configuration method to program the FPGA. So since these are already high by default, we don't have to do anything with them, and we just leave them unconnected. Next we have done, which done is a pin that will go high when the FPGA is done being configured. So it's really nice to have it go out to an LED. Next we have init B. This is used during the configuration process. The compute module needs to be able to control done, init B, as well as program B. Next we have the CFG BVS. Since this is 3.3 volts, the FPGA, this bank will be able to tolerate a 3.3 volt input from the Raspberry Pi, which is what we want because all the Raspberry Pi GPIO pins are 3.3 volt. Below that we have VP and VN. These are the leads for the dedicated analog to digital converter on the board. Next we have VREF-P and VREF-N. This has to deal with the reference voltage, which is actually all the stuff down here. And this allows the FPGA to accurately convert analog signals into digital signals. Next we have DXP and DXN. These 2 pins just need to be connected to the ground. And with that, we've actually finished everything for the configuration. So now that we've completed the configuration, let's move on to the power. So as I said earlier, I'm actually going to be using 2 different power ICs to power the board. The first one will be the ADP5054 by Analog Devices. This is a quad buck regulator integrated power solution. What does that mean? Well, the quad means that it has 4 different outputs. A buck regulator is a voltage regulator that can efficiently take higher voltages and step them down to lower voltages, which is exactly what we need. The reason why I picked this one specifically, the 4 channels is nice. They're pretty high current channels, which I'll need since the XC7A50T has more logic and will require more power. It also has really good output accuracy. It's important to have good output accuracy because any instability in that is going to negatively affect the FPGA's performance and stability. And probably the simplest thing was that under applications, it has FPGA and processor applications. And if we scroll way down here, was that it? Yes, it was. In their typical application circuit, which is a circuit that they give you to just kind of show how to use the thing, and that's whenever I'm wiring up a new IC, I usually use the typical application circuit, but just altering values that I need altered. The typical application circuit has an FPGA as the thing it's supplying power to. So I think this is a good choice. The second power IC is going to be the Analog Devices ADP2323. Now this is a dual 3 amp 20 volt synchronous step down regulator with integrated high side MOSFET. That's a mouthful. Really all you need to know about that is that there's 2 outputs because it's dual. Each of those outputs is capable of supplying 3 amps, and you can input up to 20 volts, and then it will convert it to whatever you want. Just like with the other one, this one has a plus or minus 1% output accuracy, so it's very accurate, which is good. It's got a high power output, and I think this will be perfect for what I need it for. So with the two data sheets covered, I am going to go ahead and create the circuit for the ADP 5054 and the ADP 2323. Hi, welcome back. You'll probably notice that I'm wearing a different shirt in this scene. It's because that took me a little bit longer than I thought it would, but nonetheless, I'm done. So here's the first IC, the ADP 5054. I've gone ahead and drawn out the entire schematic. I'm not going to go over every single pin connection, just kind of the general basics for how this thing actually functions. So you'll notice at the top here, I have some notes to myself for future Crispy. So I'll go over what this thing is actually powering. On the right over here, we have the 1 volt rail as well as the 3.3 volt rail. So as I mentioned earlier, this is a quad channel power supply. So there can be a max of 4 possible outputs. Now the first channel is supplying the 1 volt rail. It can source up to 6 amps of current, and this will be powering the VCC int, which is the internals of the FPGA where all the logic actually figures out what you're trying to figure out. The MGT AVCC, which this is the internals in the GTP transceivers, and the VCC BRAM, which this is powering the BRAM inside of the FPGA. That's basically the dedicated blocks for memory. Below that, we have the second channel output, which is powering the 3.3 volt supply. This is also a max of 6 amps. It will be powering the VCC 0, which is the IO bank 0, which all Xilinx FPGAs have an IO bank 0. It's not really an IO bank, it's the configuration bank. So essentially, by tying the VCC 0 to 3.3 volts, I'm setting my configuration voltage to 3.3 volts, which is what I want because the compute module uses 3.3 volts for its output. So we want that. And then to IO banks 14, 15, 16, and 35. Underneath that, we have the PCIe 3.3 volt. Now, per PCIe standards, if there's a PCIe connector, then it has to supply up to 3.3 volts at 3 amps of power through that connector. So this will be for this connector down here. This is the PCIe 1X connector that's actually connected to the compute module. So in order for this to be in compliance with the PCIe standard, it needs to be able to supply up to 3 amps of 3.3 volt power to whatever's plugged into it. So that's why that's on there. And then finally, it's going to be powering the Ethernet PHY transceiver. The Ethernet PHY is this chip here. And now if we move to the other side of the board, we have only one channel over here. I've combined channels 3 and 4 together, so instead of having 2 separate independent 2.5 amp supplies, there's now a single 5 amp supply. And this is perfect because this will be supplying 5 volts up to 5 amps of power to the compute module 4, which is more than enough power for any compute module 4 that you put on the board. I've added a power header, so the 3.3 volt, the 5 volt, 12 volt, and ground will all be accessible from this header. It's actually this one right here. So having the 5 amps on the 5 volt line will be able to power whatever you plug into that. There's also some headroom with the 3.3 volts as well. And the 12 volts, well, that's just coming from the actual power supply itself, so I'm not worried about that. Now let's kind of talk about how these power supplies actually work. So each channel has an adjustable output voltage, and that voltage is set by using a feedback pin. So we zoom in here, we'll see there's an FB3, there's an FB1, and what these feedback pins are used for is you actually connect them to a resistor divider network that is then connected to the output for that channel. So for instance here we have the feedback 1, so this is tied to channel 1, which is outputting the 1 volt power supply. So we've connected that 1 volt rail over here, and then you connect it to, we'll just call it resistor A and resistor B, and in between them, you connect the feedback pin, and then resistor B goes to ground. But essentially what happens here is you have the voltage that you want over here, and then these feedback pins want the voltage where it's reading it right here to be 0.8 volts, or whatever the data sheet specifies. In this case, it is 0.8 volts. So it will continue to adjust the duty cycle of the output, which is basically raising or lowering the voltage on the output, until this pin is reading 0.8 volts. And then it will make sure that it'll stay there no matter what the load is, up to the max supply that it can output, which in the case of channel 1 is 6 amps. I can't just use a 1 kilo ohm and a 1 kilo ohm resistor here. I actually need to do some math and some little bit of electrical engineering, V equals IR, to figure out what these resistors should be. But I haven't specified them yet because I still have quite a bit of other resistors to place on the board. And when you're designing PCBs, it's a good idea to limit the amount of unique components on the board. If you can do that, the final board assembly will be cheaper and the components in general will be cheaper because you'll be ordering more of the same component, which you get a lot of bulk discounts when you're buying electronic components. So I've held off on doing that for now. I'm actually going to draw out the rest of the schematics, and then we'll come back to this and we'll see what resistors I've used elsewhere in the board and then try to use them here. And then essentially all this IC is doing is it is turning on and off a switch really, really fast. We have an integrated circuit here that is basically 2 electronic switches. It's a dual N-channel MOSFET integrated circuit, and this IC's job is to turn on and off these switches whenever the power supply needs more power or less power. It's a fine balancing act, but that's essentially all this is doing. And that sums it up for this one. So we're going to move on to the next IC now. This is the ADP2323. Now this one is a little bit simpler. It's a bit smaller of an integrated circuit, so there's only 2 outputs to it. But it works pretty much the same way as the other one. You'll notice that there is a feedback pin and a feedback pin, and it's actually using the exact same dual channel MOSFETs that are switches just to turn on and off. But for channel 1, we have that supplying the 1.2 volt rail with up to 3 amps of current. And this is only powering the MGT AVTT, which is actually the input-output of the GTP transceivers on the FPGA. And then the next channel is supplying the 1.8 volt rail at 3 amps. This is going to be powering the IO Bank 34, the Ethernet PHY input-output, and the VCC auxiliary. VCC auxiliary is power that is internal in the FPGA that it needs. And VCC 34, the IO Bank 34, and the Ethernet PHY input-output are actually connected together. This is how the FPGA is going to communicate with the Ethernet PHY. It's going to be using this bank here connected to the input-output of this Ethernet PHY. So they need to be at the same voltage. And this bank is also going to be powering the LEDs. And with that, that's the power supplies for the board. So now we can move on to the next schematics, which the next ones will be the Compute Module 4 connectors, which as you see, I don't have anything here. I have been working to get the footprint and the schematic symbols done. But the next time you see me, I should have that done, and we will go through actually drawing out the Compute Module 4 connector schematic, as well as the peripherals for the Compute Module 4. Thanks. I hope you enjoyed the video. I'll see you in the next one.